Hello everyone. This is the first part of video lecture of section 6.2, differential equation 2540. So this is the lecture for Friday, March 27th. I'm going to split section 6.2 two parts. The first part should be covered today, Friday, March 27th, and you're supposed to study and learn as much as you can. And then I'm going to also upload second part of section 6.2, which is supposed to be covered on Monday, next Monday, which is, I think, 30th, March 30th. Okay? All right, so the homogeneous linear differential equation, this is the topic with constant coefficients. So in section 6.1, we learned that general nth order linear differential equations have a solution. There's existence and uniqueness of the solution. And then we learned that for nth order linear differential equation, if you can find n linearly independent solutions, you can get all solutions for homogeneous equation. Just a linear combination that'll form general solution. Now, if you have a non-homogeneous solution, it takes only one solution you have to find. You have to find only one solution, one particular solution, and then general solution of the homogeneous equation plus that particular solution will give you general solution of the homogeneous equation. All right? But in section 6.2, we didn't talk about how to get those linearly independent solutions for homogeneous equation. So, just like chapter 4, we will now further restrict ourselves to a case where you have only constant coefficients for nth order linear differential equation. So, by the way, as you know, I uploaded my lecture notes of the remaining sections. All right? So when you use this video, you have to print out the lecture notes from the course web page. We're going to use our regular course web page, okay, until the end of the semester. And I'm going to upload lecture videos section by section, a lot of times, split into two parts. But I'm going to use Blackboard only to collect your homework. Not homework, discussions, report of discussion, okay? Because it gives us some convenient access, especially for my grader. So, except for submitting your discussion, we're gonna use our regular course web page, including this link, uploading the link to YouTube video lecture, okay? All right, so this is the system. So I'm not going to write every single words of this lecture notes, but I'm going to write many of the comments here, which you cannot find on lecture notes. So this is the system we're working. All right. Oops, T, A1, Y prime, T, A0, Y equals 0. So, okay, wait a minute, I have to turn off the heater, it's a bit hot. All right, so here AIs are all real numbers, so constant coefficients. And obviously AN is not 0, that's why it is nth order linear differential equation. Okay? Now, in previous section, we dealt with not just the constant coefficient, but any function of t, which are continuous on a certain interval I. Then we had an existence and uniqueness theorem of the solution, that you must have a unique solution if you have obviously n initial conditions. Then you have an initial condition defined on the full interval I, on which all coefficient functions are continuous. Constant functions are obviously continuous on the whole real interval. So these are continuous on the whole real line. So by that existence in unique theorem, we know that there must be a solution, right? Which is defined on the whole real line. Okay? Now, so if we can find so n linearly independent solution, which is y1, y2, yn. Then the general solution for this homogeneous equation is this linear combination. That will cover all solutions, general solution. All right? So, in this section, we're going to take the same approach as we did in chapter 4. Okay? How to find those n solutions. Now, before we do continue, let me do two things. First of all, in second order differential equations, when you have something like this, then we found that, okay, this auxiliary equation, solution of the auxiliary equation, so r minus 4, r minus 2, plus 2 equals 0, r equals 4 and negative 2. Then we get y equals e to the 4t, e to the negative 2t. So you find two linearly independent solutions when you have two different values. But if you have something like this, your characteristic equation is r squared minus 4r plus 4, r minus 2 squared. So if you have repeated solutions, then you get e to the 2t, only one, right? Unlike this case. But then t times e to the 2t is, they form linearly independent solution. All right? And finally, if you have something like, so that would be r squared minus 4r plus 5 equals 0, r minus 2 squared plus 1 equals 0, r minus 2 squared equals negative 1, so r minus 2 equals plus minus I, 2 plus minus I, then you have e to the 2 plus, instead of e to the 2, we write it e to the 2t cosine 1t e to the 2t sine 1t, right? Then these two form linearly independent solutions. So for second order equation, you need just two linearly independent solutions. We want to do the same thing here for general order, all right? So we want to develop, but then unlike second order case, n can be very large. We don't want to fix n value. We want to develop. We want to show that these same techniques are possible regardless of the value of n, no matter how large n is. So we need to have some systematic notation, right, to deal with this in general case, to deal with the general case, all right? So in the end, we want to do similar path. We want to talk about, characteristic equations for this, and we want to talk about linear independence when you have n different roots of the characteristic equation, and so forth. Okay, so those are the first comments. Second comment is the notation. So before we delve into this, so let's say dy over dt, we can write it d for derivative. It's a convenient notation, all right? And then d squared y dt squared. Actually, this comes from this notation, actually. So d over dt is kind of a differential operator of y twice. So we write it d squared y. Okay, second order derivative. It's not the d cubed. This is d applied y. This you can consider this is like this differentiation of y and then another differentiation, right? Because this is actually the original meaning is this, right? Differentiation of y, the derivative of y, the derivative of the derivative of y. We use this also exponent notation, even though it's not multiplying. It's repeated application of that differentiation operator. Okay? So then, you know, the nth order derivative, this will be written as this way. All right? Now, this differential operator also can be combined using linear combination. For example, if you have let's say d squared y minus 4dy 5y, okay? That is corresponding to actually second order differential equation. All right? That can be written as this way. All right? So we are allowing distributive properties of linear combination of these differential operators. This is very convenient. All right? So you can consider this one as a whole is a one operator. Operator is a fancy name for a function which takes another function as an input and then the resulting function as an output. So, and then when that operator involves differentiation, we call it differential operator. So you can consider this whole thing as a one unit, let's say L, some sort of differential operator, okay, whose result is, if you give me a function, my differential operator gives you this as an output function. So operator, a fancy name of a function whose input is a function and then output is another function. Differential operator, because that operator involves differentiation of the input function. So this is a very convenient notation. All right, so we will use this notation to rewrite this equation. So this is called number one. Number one can be written as, before we write it, so we define, okay, that an okay, the left-hand side of the equation 1, using that d notation, can be written as d nth y a1 dy. Okay, so I can write it that way. So just changing d over dt with d. Okay, now that one, just like the way I combined there, you can, this is convenient, way of writing. See? As a whole, it's a differential operator working on y. Okay? So I'm going to call it L of y. So this linear combination of various order of differentiation of d, okay, differentiation operator d, is called L of y. Okay? So that definition, I'm going to call it 2. All right. Now, when you had something like this, as I wrote before, you started with e to the rt. We hope that there is a function of this exponential function form, hoping that this, with appropriate value of r, this is a solution. Then you plug it in, then r squared e to the rt minus 2r e to the rt. See, that's how you got characteristic equation, right? We want to do the same thing. We want to look for a solution of this form. Okay? So, for y equals e to the rt, we find that, okay, plugging in e to the rt to y. That means we're taking L of e to the rt. Okay? Then, now, what is this? D of e to the rt is r times e to the rt, right? Just like that. Nth order derivative e to the rt, r to the n e to the rt, right? So plug in here, what do you get? An e to the rt, d e to the rt, e to the rt. So that is basically an r to the n, e to the rt, an minus 1 rt, e to the rt. Okay? Just like we did this. Alright? We just did it with fancy notation. Alright? Now, an r to the n, just factorial e to the rt. Just the way we did here. Factorial e to the rt. Then you get this polynomial in r times e to the rt. Okay? Alright, so I'm going to call this one is polynomial in r, p of r. Okay? So p of r is a polynomial in r with the same coefficients of the given nth order linear differential equation. Instead of nth order derivative, you have nth power of r and so forth. And this is what we call auxiliary equation, just like before. Anyway, so L of e to the rt equals 0, right? E to the rt is a solution for this. Yeah, I'm gonna write this. E to the rt is a solution to number 1, right? That means when you plug it in this one into the left hand side, you get 0 for all t. Alright? Now what was e to the rt? That was this. PR. That is p of r times e to the rt. So, solution equivalent to this. Okay? Which is equivalent to this. But e to the rt is not 0. Never be 0. That means p of r must be equal to 0. Just like the second order case. characteristic equation. Alright? So this is called auxiliary equation or characteristic equation. Alright? Or characteristic equation. And this is called auxiliary polynomial or characteristic polynomial. Alright? So, in order to find the solution of this form for this equation, you have to solve this equation. Now, P of R is, what is it? The nth degree polynomial. Okay, with real coefficients. Now, when you have n degree polynomial, okay, look at the facts in the lecture notes. By fundamental theorem of algebra says that if you have a polynomial equation of degree n with real or what complex coefficient, you must have n solutions, right? Some of them may be repeated, but anyway, if you count up to multiplicities, triple roots as a 3 roots, double roots as a 2 roots, then you have exactly n roots in complex number system, right? It could be real, it could be imaginary, but the bottom line is that n degree polynomial equation has n roots, all right? So, okay, by the way, it turns out that this looks like exactly P of R, except that R replaced with D, isn't it? Right? So, note that L can be written linear combination various order of D, you just write P of D here, okay? L of P of D. Now, okay. So, according to fundamental theorem of calculus, this one must have n zeros, called R1, R2, all the way to Rn. Okay? Some of them might be repeated, some of them just different, distinct, but I just count exactly n zeros. Alright? That means, therefore, P of R can be written as, now, R minus R1, R minus R2, all the way to R minus Rn, and then leading coefficients A. Okay? Therefore, your L would be P of D. And you can write this one is just like, now, polynomial can be factored, then linear differential operator also can be factored, same way. And I'm going to show you what that means shortly. Okay? So, what does it mean by factored form of a linear differential operator like this? And this is the meaning. So example, in the lecture notes, consider second order differential equation. Consider this. Now, I can write this one as L of y equals 0. So L of y as, okay, d squared plus 3d minus 10y. Okay? Now, corresponding characteristic polynomial is r squared plus 3r minus 10, which is r plus 5, okay, factoring this, r minus 2. Alright? Now, Then what does it mean by factor form? Okay, d plus 5 and d minus 2, all right? So what does it mean by this? Okay, now this means that d plus 5 operator, first of all you have to do right next operator, which means dy, derivative of y, minus 2 times y. And then the distributive law, d of dy minus 2y plus y times dy minus 2y. And what do you get? d of dy, second order derivative. You could call it d squared y. It looks like a multiplication, but you know, it's a twice differentiation. Differentiation twice. So it works like it. 10y, right? This is, you can write it. So, same as, right? So what I'm trying to show is that when you have a factor form of differential operators like this, you have to apply this one first, and then followed by the next, and followed by the next. You take, it's just like a composite function, right? Composite operators. But then when you do this, the way this one distributes is exactly the way we distribute factor form of polynomial, isn't it? Right? It works like multiplication, even though it's not a multiplication, it's a derivative of derivative, second order derivative, but it works like multiplication. So it follows the same distributive rule. That's why you can write your linear operator in this vector form. You could do it so you can write it this way or this way. This is exactly the same thing, right? That's what I'm trying to say. You could apply differential operator on y like this or factored form. The result will be same because the way this distribute will be exactly the way polynomial distribute. Okay, that's the point here. All right. So anyway, here L is same as d plus 5, d minus 2. When this is L, all right. All right. Now we are ready to. Now with this fancy notations, we can take care of this general treatment of the theory of homogeneous linear differential equation with constant coefficient. Okay. Now, by the way, I have to check the video from time to time. All right. Now, lemma. Look at lemma. So, if R1, R2, all the way to Rn are distinct, real or complex, either way. Real or imaginary, that would be better. Imaginary. Any complex zeros. Roots of auxiliary equation. Then e to the r1t, e to the r2t, all the way to e to the rnt are not only solutions but linearly independent solutions to this number 1. See? This is the first major one we want to do. Okay? The way we did with short examples I did, as I recall. Alright? Now, how do we prove this? Okay? We already showed that they are solutions. That part is from we already proved it, right? E to the RT will be a solution if R is a root of this characteristic equation. The question is, how do we show linear independence? Okay? When n is not fixed number, n can be any large number. How do we show this one in general way? Okay? That is a big question. That's why we developed all these fancy notation. Alright? Okay. So, proof. The solution part is already done. The linear independent part. How do we prove linear independence? Now, we have to develop, okay, let's say P of R is AN R minus I1. Okay? So because these are the distinct linear, distinct zero of this equation, distinct roots of this equation. So you can factor P of R like this. Therefore, your L, linear operator L, this is L of y equals 0. Same thing. Is P of D, as we saw here, P of D. That can be also written as AN D minus R1, okay? Just like, polynomial. D minus Rn, okay? Okay. Now, we're gonna, in order to prove linear independence for this one, for general n case, we developed some clever trick here. For any integer k, such that anything between 1 and n, okay, we define p sub k, kr. So, okay, it's like this. Okay, p1 means that out of this you drop this, everything else. That would be p1k. p2k, did I say p1k? I'm sorry, p1 of r. p1 of r is everything except for this term. an times r minus r2, r minus r3, through r minus rn. P2 of r will be everything except for the second vector. So pkr is defined as same as p of r, except that up to k minus 1, and then jump to k plus 1. See? Only the kth factor is missing. Okay? That is pk of r. And obviously lk, we can define lk exactly the same way. lk is pk of d. Alright? As just like L is P of D, LK is PK of D. So that means AN D minus R1 D minus RK minus 1 D minus RK plus 1 and D minus R. Oops, dot. Okay? That's the notation we're going to need. So, now we are ready to tackle on the linear independence. What was the definition of linear independence? That is, if you have a magically disappearing linear combination, C1 e to the R1t plus C2 e to the R2t, all the way to Cn e to the Rnt equals 0 for all t, then all the coefficients C1, C2, C3, all the way to Cn must be 0. Alright? then we say that they are linearly independent, which means there is no magically disappearing linear combination for those functions. The only way you can make them disappear through linear differential equation is by having zero, trivial linear combination only. All right? So we want to prove that. So we have to start with this. So suppose, so to show linearly independence, we suppose that C1 e to the R1t, see, Cn of e to the Rnt. Okay? So as I said, this is true for all t. Okay? Let's say you have a magically disappearing linear combination. And then what we want is somehow we have to show that this means only one thing. That is, every coefficient must have been zero. Okay? That's what we want to prove. So let's do that using this clever operator. Okay. Now, okay. So for any given k, okay, let's consider we take LK of both sides of this. LK of C1 R1t, C2 e to the R2t plus all the way to Cn e to the R and t. So you take LK of this equals LK of 0. Okay, zero function LK will be, well, constant zero function. Okay? Now, then, because LK is also linear operator, it can be easily shown that, superposition principle or linearity. You can split over addition, constant can be taken out of it. C2 LK of e to the R2t. Cn LK e to the Rnt equals 0. Okay? So I'm going to call it number 4. So keep it. This is number 4. Now, in other fronts, LK of e to the R. So, e to the R. So just think about this, what that means. LK e to the RT is, we know that then its own characteristic polynomial will come out. Pk of R e to the RT, right? Just like e to the L of e to the RT equals P of R e to the RT. This is n-1 order differential operator. So LK e to the RT will be Pk of R e to the RT. Okay? So, which means R minus R1. Okay? All the way to R minus RK minus 1, R minus RK plus 1, R minus Rn e to the RT. Okay? So because of this, now, note that, look at this. If I is not same, is different from k, then if I is different from k, what happens? pk of ri is what? Instead of r, you have to put ri. ri minus r1, ri minus r2, I minus rk minus 1, k plus 1. So, now, here only kth term is missing. Kth factor is missing. But if I is not same as k, i's factor will show up somewhere, right? Somewhere you will have hit ri minus ri somewhere shows up, right? Somewhere. I don't know where. Somewhere ri minus ri will show up and equals 0. Okay? So for example, P3 of R2 will be 0 because R2 minus R2 will show up. P10 minus R5, well, R5 minus R5 shows up before you have a missing 10th factor. Alright? So this is the case. So all of this are just okay. Now, because of this, what can you say? Therefore, Lk of e to the rit equals pkri e to the rit, right? Instead of r, you put ri, because it is 0. For all I, which is not equal to k. Alright? Okay. But if you have exact match e to the rk of t, what about this? That is pk of rk e to the rk of t. Okay? Now what was this? Rk minus R1, Rk minus R2, k minus Rk minus 1, Rk minus k, k plus 1, n. So this is kth term is missing. Alright? Instead of R, you have R sub k. Now, because we are assuming that all ri's are distinct, rk minus r1 is not 0 because they are different. They're different, so it is not 0. You could have gotten 0 if you had rk minus rk, but that case factor is missing. So everything is not 0. This is not 0. This is not 0. All the way to the end. Okay? Oh. Times e to the rkt. Okay? So anyway, this is not 0 for all t. Okay? 4. And what is 5? So this is 5. And this result is 6. Alright? Then now we can conclude. Alright? So what do you get? For all this here, what was it? Now, look for this. For CLK, R1, okay? When you have different index, you get 0, right? Let's say k equals 3. Then L3E different from 3. C to L3 of e to the R2k also 0. But then C3 L3 e to the R3k will not be 0, right? So, by combining 4, 5, and 6, everything will be 0 except this term. Okay? And then we found that from here, this is not 0. That means CK must be 0. Okay. I know that this is very confusing. I admit. But this is a general way to handle this proof. When you have magically disappearing combination, every constant must be 0. Now, your CK is any given k. Since k can be anything, therefore C1, C2, everything. So you start with this one at L1 of this proof. Okay, C1 is 0. Now, what about L2? C2 equals 0. L3 of this, through going through this, C3 equals 0. That's why you can do this. Every coefficients are 0. Okay? So this is a fancy way of doing this. Now, if you know linear algebra, actually, you can do this one by taking derivatives. Well, anyway, there's other ways. But your textbook chose this, this method using some clever linear differential operators. So in the end, we just prove that this is, if you have a distinct complex roots of the equation, you have linearly independent solution. Therefore, I'm going to finish this part 1, theorem 1. So basically, using this, if you combine it, C1, Y1 of T, I'm not going to write the entire statement, this theorem 1, distinct root case. So, you can get general solution for nth order linear differential equation by using, not Y1, sorry about that, R1T, C2 e to the R2T, Cn e to the Rnt. So again, just like a second order case, it's a matter of solving n degree polynomial equation called characteristic equation. Okay? And when those roots are all distinct, then they are linearly independent. And just like the second order case, if some of them are imaginary roots, then they always come in complex conjugate pair. That is well-known fact. Because we consider all these AIs are real number. When you have a real coefficient n degree equation, and if you have a linear, imaginary root, they come complex conjugate pair, coming continuous conjugate. So if 2 plus 3i is a root, then 2 minus 3i is also root. So if one of them, let's say r equals alpha plus beta I, then there's some, let's say rj, rk, then there are some other things will be complex conjugate. Alright? For those cases, combine, instead of cj e to the rjk plus ck e to the rjt, okay? Instead of this, we can replace this one as dj e to the alpha t cosine beta t, dk e to the alpha t sine beta t.
exactly the way we did in second order differential equation, right? When you have a 2 plus minus 3i, then e to the, this one t equals e to the 2t cosine 3t plus I times sine 3t, so you have cosine 2t sine, e to the 2t cosine 3t, and e to the 2t sine 3t, right? Just like that. So if you have, so here, these CI's are all complex numbers. It's a complex number. But if you have a complex conjugate roots for Rj and Rk that match, then for those one we can replace with this. Alright? If you have a real roots, then use real coefficient. If you have a imaginary roots, then use complex conjugate coefficient. Then if you choose Cj and Ck are complex conjugate coefficient, then everything will be, written in real coefficient with this, right? Okay, so that's the end of the first part of the lecture of section 6.2, and then we will finish the section 6.2 in the second part, which will be uploaded by Sunday night. So that would be supposed to be, that should be done by Monday, okay? All right, so, well, thank you, and I'll see you next time.